I'm Sarah.
I'm Jasmine,
I'm Stephanie.
and we chose to do our final project on the history of mathematics, and we focused on Pierre de Fermat because he definitely had a big impact on mathematics and especially calculus as a whole.
Some of his main studies were optics, number theory, finding maxes and mins. So we're learning about that now, so we find it very interesting.
Okay, so Pierre de Fermat, he was born on August 17th in 1607, and he died in 1665 and lived 57 years. He was originally a French lawyer at the Parliament of France, in addition to his hobby of mathematics. For his childhood, he grew up alongside with one brother and two sisters, and for his undergrad, he attended the University of Orleans, where he received his Bachelor's of Law, and not mathematics. He had a love for mathematics, but he did not let his love completely take his time away from his practice of law. When he retired, he devoted his life to mathematics, and one of his first principles was he provided a law for light, which pretty much explains why light will reflect off of a mirror or any surface, and that's known as Fermat's principle. Him and Pascal also discovered the theory of probability. Although Fermat had many theories, principles, and several revelations within the mathematical world, he did not publish his discoveries, so that's why he's not typically referenced as the first person to discover his works, but his work still withholds within the mathematical community.
The most well-known theorem that Fermat came up with is the Fermat theorem of extremas. It states that if the function f is differentiable and the point a comma f of a is an extrema on f, the derivative of f of a is 0, provided that f of a exists. So in order to know what an absolute maximum is, it's that x equals 0 if f of x is less than or equal to f of c. And an absolute minimum is at x equals c if f of x is greater than or equal to f of c. So we all know the function y equals x squared, and in this graph we have a minimum value at 0, 0. So we could prove this by doing Fermat's theorem, which states that if you take the derivative of a function of x squared, which the derivative of x squared equals 2x, and in order for Fermat's theorem to hold true, you have to set that derivative equal to 0 and solve for x. So in order for this function to be 0, x has to equal 0 also. So we draw a number line with the critical value 0, and we test the numbers in the derivative. So if we plug in a number less than 0, say negative 1 into the derivative of 2x, we get a negative value. And then if we plug in a number greater than 0 into the derivative, we get, say, 1, we plug in it, we get a positive number, and that's 2. So that states that if the function is decreasing, then increasing, we're going to have a local min. Now we can look at an equation that we might not know off the top of our head. And this equation, f of x could be equal to 2x squared over x squared minus 1. So in order to follow Fermat's theorem, we have to take the derivative of this function. So f prime of x equals the derivative of the top, which is 4x, times the bottom, minus the derivative of the bottom, times the top, over the bottom squared. So the derivative simplifies to negative 4x over x squared minus 1 squared. And Fermat's theorem says that to find the critical values, you have to figure out where the function is equal to 0 or does not exist. So the function is equal to 0 when the numerator is equal to 0, and that's at x equals 0. And that's one of our critical values because the denominator, it doesn't exist when the denominator equals 0, and that's at negative 1 and 1, but that is not in our domain, so we don't have to worry about that. So our critical value is 0. So when we test points into the left side of 0, negative number, we're going to get a positive over a positive, which is positive. And then on the right side, we're going to get a negative over a positive, which is a negative. So here we have a local max at x equals 0 because the function is increasing and then decreasing.
Okay, so now we're actually going to get into the proof behind Fermat's theorem that Stephanie was talking about earlier. So first part of our proof, we're going to assume c comma f of c is a local max, then f of c is greater than f of c plus h for any small h. So if f of c plus h minus f of c is less than 0, and f of c minus f of c over h is less than or equal to 0 over h equals 0. So this kind of is like the definition of a derivative, if that doesn't look familiar to you, and this directly is the definition of a derivative, but now we're applying the squeeze theorem. So the limit as h is as approaching 0, f of c plus h minus f of c over h is less than or equal to the limit as h is approaching 0 is equal to 0 because 0 over h is 0, and then that proves that that will be equal to 0. So that's pretty much proving that the derivative is equal to 0. And now we're going to assume that h is less than 0. So we're looking at a local min, and we're going to follow the same steps, except now the inequality is switched because we're looking at h is less than 0. Okay, so now when we continue the steps of the squeeze theorem, we find that the limit is greater than or equal to 0, and which is the derivative of f of c. So based on the squeeze theorem, 0 is greater than or equal to f of c, which is greater than or equal to 0. Thus, the f prime of c equals 0, proving Fermat's theorem that the derivative must be equal to 0.
Another main topic that Fermat delved into was integrals. So he looked at the idea that we know how to take a derivative, but he wanted to do antiderivative. So if we have the function x squared, to find the derivative, we would simply add 1 to the exponent and divide by that exponent plus c. So he proved this by taking the derivative of this, which would be 3 over 3, x squared. This is just 1, so that would be x squared. So it works out. So the formula that he used for this was a to the n plus 1 over n plus 1. So on top of this, after he was working a lot with integrals, he did overestimation of graphs. So if we have a graph that looks something like this, he would use overestimation of rectangles, which would look like this, and so on. This helped him. He would find the area of each rectangle, and then that would get him like a close value to what the actual area was equal to. In addition to Fermat's other studies, he also used his theory of maxima and minima, which we showed earlier, to show that the law of refraction is constant. He showed that light traveling between two paths seeks a path that has equal waves, not necessarily the density of the medias that the light is traveling between. Also, he worked with sums of powers of positive integers, which helped him decide deduce how sides of triangles, for example, are related. This just shows that Fermat had a major impact in not only one specific category of math, but multiple, and he really had a big impact on the math community and the overall intelligence.